Okay, let's state another theorem. So the sequence r raised power n is convergent if r is between -1 and 1 and divergent for all values of r. So this to say that limit as n approaches infinity of r raised power n is 0 if r is between -1 and 1, is 1 if r is exactly equals to 1. And then we'll give another definition. A sequence an is called increasing if an is less than or equals to an plus 1 for all values of n greater than or equals to 1, i.e. a1 is less than or equals to a2, less than or equals to a3, less than or equals to a4, less than or equals to the next term in that order. And then we say a sequence an is said to be decreasing if an is greater than or equals to an plus 1 for all n greater than or equals to 1. And then you say a sequence is called monotonic if it is either increasing or decreasing. So we'll list a few examples now to illustrate this. So the first one, you say the sequence an where an is given by 3 over n plus 5 is decreasing because three over n plus 5 is greater than 3 over n plus 1, i.e. 3 over n plus 5 is greater than 3 over n plus 6. This inequality is equivalent, so actually for all n greater than or equals to 1. The right hand side is smaller because it has a larger denominator. Good. And then another one, number 2, in form of a question, show that the sequence an where an is given by n over n squared plus 1 is decreasing. So solution for this just make use of the definition of a decreasing sequence. So we say we must show that an plus 1 is less than or equals to an, i.e. n plus 1 over n must be less than or equals to n over n squared plus 1. So we can always cross multiply to have to rewrite this inequality. So we have n plus 1 over n plus 1 square plus 1 less than or equals to n over n squared plus 1 is equivalent to n plus 1 times n squared plus 1 less than or equals to n into n plus 1 square plus 1. So when you open, we have n cubed plus n squared plus n plus 1 less than or equals to n cubed plus 2n squared plus 2n. Now, in simplifying, this one becomes 1 is less than or equals to n squared plus n. So it should be obvious to everyone that n squared plus n must be greater than or equals to 1 for n greater than or equals to 1. So therefore, an plus 1 is less than or equals to an, and so is decreasing. So just show from definition of decreasing. And then number 3, show that f of n given by n over n squared plus 1 is decreasing. So solution for this, we consider the function f of x equals to x over x squared plus 1, and then derivative of this function is x squared plus 1 minus 2x squared over x squared plus 1 square. It is 1 minus x squared over x squared plus 1 square. And then this thing is less than 0 whenever x squared is greater than 1. So thus, f is decreasing on this interval, and so f of n must be greater than f of n plus 1. So therefore, this was supposed to be labeled an. And therefore, an is decreasing. So let's give another definition. A sequence is bounded above if there is a number m such that an is less than or equals to m for all n greater than or equals to 1. And then it is, we are referring to the same an, it is bounded below if there's a number small m such that this small m is less than or equals to an for all n greater than or equals to 1. And then next statement you say if it is bounded above and below then an is a bounded sequence. So those are the definitions. Then we say so can just say, for instance, the sequence an equals to n is bounded below an greater than 0, but not above. And then next we say the sequence an equals to n over n plus 1 is bounded because zero is less than an less than 1 for all n. So next statement that we need to remember is that, so we know that not every bounded sequence is convergent you can put in brackets an equals to negative 1 raised to power n satisfies negative 1 less than or equals to an less than or equals to 1, but it is divergent I've seen this one before, and not every monotonic sequence is convergent. E.g., an equals to n approaches infinity. But if a sequence is both bounded and monotonic, then it must be convergent. So this is what we call completeness axiom. Completeness axiom for the set of real numbers. So it states that if S is a non-empty set of real numbers, that has an upper bound then S has a least upper bound So this is to say B is an upper bound for S, but if M is any number, any other upper bound, then B is less than or equals to M, so maybe just from layman's point of view, you can just say the completeness axiom is an expression of the fact that there are no gaps, or there is no gap or hole in the real number line. So theorem every bounded monotonic sequence is convergent. So proof. So let's suppose n is an increasing sequence. So since n is bounded, the set S has an upper bound. That's from definition. Upper bound, call it L. So given an epsilon greater than 0, L minus epsilon is not an upper bound. For S, since L is the least upper bound, so therefore an greater than L minus epsilon for some integer n. But the sequence is increasing, so an must be greater than or equals to a capital N for every small n greater than capital N. Thus, if n is greater than capital N, we have an is greater than L minus epsilon. So 0 is less than or equals to L minus an less than epsilon, since an is less than or equals to capital L. Thus, L minus an is less than epsilon whenever n is greater than capital N. So limit as n approaches infinity of an equals to L. So that's the end of the proof. So let's do a quick example here. So investigate the sequence an defined by so there's a problem. So the solution will be we begin by computing the first few terms. So A1 is given as 2. A2 will be a half of 2 plus 6, which is 4. A3 will be a half of 4 plus 6, which is 5. A4 will be a half of 5 plus 6, which is 5.5. A5 will be a half of 5.5 plus 6, which will be 5.75. A6 will be 5.875. A7 will be 5.9375. A8 will be 5.96875. So then from these few terms, we can actually discover something. So these initial terms so this is what you can see from these few terms. So then we can actually say, so we can also using mathematical induction to show that this is from definition of increasing. So when n equals to 1, we have A2, which is 4, is greater than A1. So if we assume, this is the process of mathematical induction. If we assume that it is true for n equals to k, then this is the hypothesis step on the mathematical induction. We have ak plus 1 greater than ak. So ak plus 1 plus 6 must be greater than or equals to ak plus 6. And a half into ak plus 1 plus 6 must be greater than a half ak plus 6. Thus, ak plus 2, ak plus 1. So by doing this one now, so we have deduced that an plus 1 is greater than or equals to an is true for n equals to k plus 1. So therefore, the inequality is true for all n by mathematical induction. So the last step now, we need to show that the sequence is bounded. So next, we show that an is bounded by showing an is less than 6 for all n. So since the sequence is increasing, we already know that it has a lower bound an greater than or equals to a1 equals to 2 for all n. So we know that a1 equals to 6 is less than 6. So the assertion is true for n equals to 1. Now suppose still there's 3 steps of mathematical induction. So suppose it is true for n equals to k, then ak is less than 6, ak plus 6 is less than 12. So a half into ak plus 6 must be less than a half into 12, which is 6. Thus, ak plus 1 is less than 6. So this shows that an is less than 6 for all n. So remember, this is by mathematical induction. So since the sequence is increasing and bounded, then by theorem 10, it has a limit. So limit equals to limit as n approaches infinity of an exists. So we have to calculate it now. So limit as n approaches infinity of an plus 1 equals to limit as n approaches infinity of a half into an plus 6, which is the same as a half limit as n approaches infinity of an plus 6, which is the same as a half into L plus 6. Now, so therefore, since an approaches L, this implies that an plus 1 approaches L2 as n approaches infinity, n plus 1 approaches infinity. That's why we are saying that this is the same as this. So we have L equals to a half L plus 6 So solving, we get L equals to 6. So that's the end.